Okay, so I'd like to first of all thank the organizers for this very honorable invitation. It's a real pleasure to be here. I have been at EFTF conferences before. Some of them, I think the last one, however, was in Besançon. That dates back more than about a decade. So what I'd like to do this morning is tell you about a development that's ongoing, not just in my laboratory, but really in many labs around the world, which is to develop actually new components in integrated photonics. I'd like to tell you about work that we've been doing in our lab at EPFL, also with collaborators, on developing chip-scale combs and also new technologies such as Erbium, chipscale amplifiers, or low-noise lasers, and tell you also about new developments and new materials. So first of all, if you have any questions or comments, I'd like to mention this, I'm happy to interact. Unfortunately, I cannot stay actually here the entire day, but if you have, please do email me. I'm happy in case something raised your interest. And up front, also I mentioned a couple of disclosures that have been mentioned actually in the introduction. So first, to set a bit the stage for a lot of the motivation that we have for our research, let me mention that it is quite remarkable that when the laser was invented in 1960 by Ted Malan, it was called an invention looking actually for a problem. And I think we all agree that coherent laser light has really revolutionized science and technology. We could not imagine the internet without having the invention of the laser. We could not imagine optical coherence tomographies that, for instance, measure your retina without the invention of the laser. We could not imagine the world's most accurate atomic clocks that use 1 second in the age of the universe without the invention of coherent laser light. So it's truly a technology that has revolutionized many aspects of our living, from clocks, from spectroscopy, LiDAR, and more than 50 Nobel Prizes, including the one last year, actually make use of coherent laser light. But there's one aspect actually that's quite remarkable too. In fact, if you look at how lasers are manufactured, those are still manufactured actually with very similar principles that were used 50 years ago. Okay, and what do I mean by this here? If you look, for instance, into lasers used, for instance, in AML physics, also in this community here, these are still built using legacy technology based on mirrors, on gratings, and optical fibers. In fact, there's a huge performance gap that exists between the most scalable lasers that are utilized today and actually lasers as used in many science and technology applications. And so what are, first of all, the most compact lasers that exist? The most compact lasers that exist are used in silicon photonics. Many of you have not heard of them, but you utilize them every day. In fact, they're used in so-called pluggable optics in data centers. Ethernet cables are connecting kind of server racks, but it's not an Ethernet cable, it's actually an optical fiber. And what sits at the end of the optical fiber actually is a transceiver, and that transceiver actually uses silicon photonics, so silicon edge circuits to guide light, to manipulate light, and also to generate light, to transmit over actually short distances. Now, the problem, however, with that technology is that even though it's very scalable, deployed by millions, these integrated lasers based on silicon inherently do not compete in terms of power, spectral coverage, and also their frequency agility. And so there's a huge technological gap that has opened, that's been closing over the last 10 years, and that is to make very compact integrated photonic lasers. Now, admittedly, not every application needs compact lasers. But if you think about truly pervasive technologies that every one of you uses, okay, to make a technology truly pervasive, scalability and compactness is of utmost importance. Okay, it determines kind of if you can use something kind of in your car, in your phone, or in deployable technology. So first of all, why can't you do this with integrated photonics based on silicon? That's a very mature field. Now, the reason is silicon itself. Okay, silicon is a material that is perhaps the most commercially exploited material you can think of. Okay, there's been hundreds of billions of dollars of investment to create microelectronic industries, to create highly integrated kind of electronic components. But as ironic as it may sound, despite all these investments, silicon is not a very good material for optics. And so it has several fundamental deficiencies. It has a band gap of 1 eV, so it can't penetrate the visible. And even if you use the most advanced foundries, like global foundries as one example, and you tape out basically an integrated photonic circuit, the losses that you have are typically on a level of dB per meter. So despite all these investments, okay, the very high index contrast, the edge roughness leads to very large losses in silicon photonics. Also, silicon has limited power handling, and also you can't access the kernel linearity, which gives rise to fundamentally new operation principles, some of them which I outline here. And so how can you generate really low loss integrated photonic circuits with materials beyond silicon? And that has been a challenge that over the last, say, decade, it really has fallen. And if you look what can be done today in optical fibers, I'd say it's truly remarkable. Optical fibers have losses of 0.2 dB per kilometer, whereas integrated photonics within silicon is like 0.1 dB per centimeter. So there's a 5 orders of magnitude kind of gap between the two. And so what I'd like to tell you about actually in this presentation is mostly about kind of two classes of materials. The first is a very well-known semiconductor material but new into optics, and that's silicon nitride. I'd like to show you actually that this can allow circuits that don't close the gap to optical fibers. In fact, we still have basically 2 or 3 orders of magnitude to go, but we can now make circuits that are a factor of 100 lower than what you can do in state-of-the-art silicon photonics. And so we have now losses that are not dB per centimeter, but really dB per meter. Now, what does this enable? There are some fundamentally new technologies that you can address with this. You can make, for one, very narrow line width lasers, and I'll give some examples that compete or and outperform the most coherent lasers based on fibers. You can make compact optical frequency combs by using the kernel linearity, and also you can make erbium doped amplifiers on chip, and also even traveling wave amplifiers based on the kernel linearity. And so these are what's really part of a wave of development that's ongoing that I like to call next generation low loss integrated photonics. That is going into materials beyond silicon. And I'll mostly highlight silicon nitride that we worked for last decade. It's now commercially available also. But I'll also mention in this presentation other materials, in particular lithium tantalate and lithium niobate, which are very well-known materials also in this community. They're used for MEMS filters. But actually they enjoy very beneficial properties for integrated photonics. And there's also new ways to modify these materials, including ion implantation, to create actually active medium. And so the first thing I'd like to really mention is how can you make really low loss integrated photonics? And that's what my research group and also others in the field have been interested in for the past decade. And so how can this be done? So the first is we moved to a material called silicon nitride. And silicon nitride actually is a material that's very well known in the semiconductor industry. It's used as an edge stop layer or capping layer. It's also used as a stressor layer actually for silicon transistors. And it's used as a stressor layer because you can deposit it with very high innate stress, like a gigapascal, using chemical vapor deposition. And so traditionally in semiconductor industry, these films were employed on the level of tens to 100 nanometer. And if you go beyond 100 nanometer, these materials crack. And that's why actually it has been very challenging to create tightly confining integrated photonic circuits based on these materials for many years. Now, in terms of optical properties, actually there are a few very notable ones. You have a high effective nonlinearity, bandgap of 5 eV, so you can penetrate to visible. And the material is also space compatible and can be simply deposited by chemical vapor deposition. So how can we create really low loss waveguides from this material? And so what we have overcome is one of the key challenges in this material, which is crack formation. So if you grow a few hundreds of nanometers of these films to confine light, cracks form due to the very high stress in the material. So while beneficial, say, as a stressor layer, this of course is catastrophic in manufacturing of integrated photonic circuits with low loss. So the way you can actually overcome this is actually using two tricks. Okay, and so the first trick is we actually make, instead of etching the silicon nitride, what we do is we take an oxidized silicon wafer, okay, we etch trenches, and these trenches serve as kind of stress release layer. So there's very high stress that builds up in the film, relaxes due to the presence of trenches. In addition, okay, to trenches, we also build and make kind of etch waveguides into the glass itself. And glass we can etch very well, it's a very well established chemistry to do that. And so what we do next is we fill those trenches with silicon nitride and also the stressor layer. And then we polish it. And that technique actually is known in the semiconductor industry. It's called copper damascene process. You use it actually to make electronic interconnects, where instead of filling the patterns that you etch with the dielectric material as done here, you fill them with copper. And use exactly the same step of the polishing. So this copper damascene process we actually employ in integrated photonics, and we can make that way very tightly confining, low-loss integrated photonic circuits that we commercialized with Leitentech about 8 years ago. And these actually are now manufactured in state-of-the-art 200mm lines in the X-Fab in Paris. Now, how low does the loss go with these structures? The loss we can get with these structures is about 10 dB per meter. So very significant advance over silicon. but still not really at the level of where we would like to be. Now, a few things about this Damascene process. For the experts, it's a crack-free, reliable fabrication, wafer scale, very high waveguides, even micron scale is possible, and we have a top planar surface that we can also use to transfer other materials like ferroelectrics. Now, to create waveguides with exceptionally low loss, we use one more trick. And the trick we use is that glass, in contrast to silicon nitride, starts actually to soften at 1200 degrees. So we can take the preform of glass and just heat it up to glass softening transition, and thereby actually take out all the roughness actually from the etching. And this way we can make waveguides that have exceptionally low loss. And how low is the loss that we can make? What you see here is a 1-cent coin. The chip, the upper one, is 5 by 5 millimeter. And what's shown there is a 1 meter spiral coiled up into 2.5 by 5 millimeter. So you can see the very dense integration we have. The losses here actually are below 1.5 dB per meter. So in terms of quality factor Q of the resonators, that corresponds to resonator Q is actually of 30 million in a device actually on chip. And so those are exceptionally low losses that allow us actually to harness novel functionality, which I'd like to outline in this presentation. So so in a nutshell, starting, as I said, from the use of silicon nitride in the CMOS as a stressor layer, we can now actually use silicon nitride to generate optical frequency combs. The material has been commercialized, transferred also to foundry. And I'd like to highlight in this presentation like 3 applications of this material, in particular making very low noise laser, making chip scale, actually optical frequency combs, and also optical amplifiers using rare earth ions. And so this is really opening up many new applications. To give you an example of also how wide some of these applications are and also how unexpected, let me just mention one that I also only mentioned here at a very high level. We've used integrated photonics recently with collaborators Klaus Ropers in Göttingen in a very new field, electron microscopy. We've shown actually they can insert microresonators in a state-of-the-art TM and use the optical field actually inside high-Q resonators to manipulate electron wave functions. Now, I will not go into detail of this part of the presentation, but I'd like to mention that now integrated photonics is transcending into many different new applications, some of them actually which are very surprising, like electron microscopy. Silicon nitride is also being used extensively for photonic quantum computing. Even though I'm not a believer in this field, I still think it's very fascinating to see what kind of quantum experiments you can actually do. This is an example of a quantum circuit with many photons on a programmable chip. This is work actually that was published a few years ago by Xanadu, a Canadian startup. And the chip actually you see in the background here was actually manufactured here in Switzerland. It's actually made from silicon nitride and used 4F mixing to generate photon pairs. So it's an example of a photonic quantum processor based on this material. Now the first application I would like to highlight is chip-scale optical frequency combs. And so I think to the community of researchers here, I don't have to motivate the tremendous advances in timekeeping, that have been possible by optical frequency combs, which linked the RF domain to the optical, and also conversely allowed the optical standards to be transferred into radio frequency signals. And it's really a truly revolutionary technology that's been developed by Ted Hensch and Jen Hall and many others over the years, and is now commercially employed and deployed even in space to create compact optical clocks. Now, one aspect, however, is interesting to note is that optical combs have numerous other applications where one can really benefit from a very compact form factor. And what has happened over the last now almost 2 decades is there's another approach that has been widely studied, which is called carrier frequency comb generation. And this carrier frequency comb generation allows to create very compact optical combs directly actually from chip-scale microresonators. And this allows 2 things. First of all, it allows very compact devices that can be wafer-scale manufactured. But what's more interesting, it also allows to get very high repetition rates. So repetition rates in the tens of gigahertz, which is directly commensurate actually with the microwave domain, and also allows to directly address each individual comb teeth. And so these new technologies really have the potential to make optical frequency metrology truly ubiquitous. And so if you think really about a portable optical atomic clock, having very compact kind of RF to optical links will be an integral part. And so this has been intensely studied actually over the last almost now 20 years by numerous research groups. And the vision there is really to create an RF to optical link on a chip as shown in this image. Now very briefly, how are these actually generated? The generation principle of carrier frequency combs is based on optical microresonators. To show you also a bit how far the field is advanced, let me give an example. making a high-Q resonator actually some 20 years ago was more art than science or technology. So this is an example actually of a laser reflown toroidal resonator made from glass that's a few tens of micron in diameter. And this device was residing on a chip and had quality factors of 100 million. And these quality factors are now almost on par with those that we can manufacture actually at scale using this Damascene process. And so these devices actually, despite being very simplistic, have a couple of very interesting aspects. One is they have a mechanical mode that couple to radiation pressure, which we'll not discuss. But the other part is glass itself has a kernel linearity. And this kernel linearity, okay, once you pump the material strongly enough, can give rise to photon pair generation. And so this was discovered really, as I said, now 20 years ago in optical microresonators. So when you pump a microresonator, actually a CW laser starts to generate signal-idle sidebands due to this parametric frequency conversion process. And one aspect that's actually interesting about that process is that even though the kernel linearity is exceedingly weak nonlinearity, the threshold for parametric oscillators scales actually inversely with the quality factor squared. And that is because this device has a nonlinear gain mechanism. So the higher the intensity, the larger is the gain. In a conventional laser, you have a 1/Q dependence. And so this implies if you have a very high Q resonator, you can really drive down the threshold of these parametric oscillations actually to levels of just a few milliwatts. And that was possible in this early work. Now this process can cascade, and this cascade actually gives rise to what we now understand are modulation stability combs, and can convert directly a CW laser into an equidistant set of lines. Now, you can not only generate optical combs in frequency domain, but you can also actually create optical pulses. And the way this works is using another piece of physics, and that's a piece of physics called soliton formation, or dissipative Kerr soliton formation. And so we discovered this process already, again, about a decade ago. It's a very striking process by which when you pump a crystalline resonator, shown in this picture, with the continuous wave laser, what you find is that the resonator itself, when you start pumping it, generates many sidebands. But at some point, actually, the waveform inside the resonator becomes chaotic. And when you tune actually through the zero crossing of the resonator, from the blue to the red detune side, you see actually a series of steps. And these steps actually are commensurate with the resonator starting to form actually optical solitons. And so the governing equation actually of this system, so how to describe the field interacting with the nonlinear material, is given by a nonlinear Schrödinger equation, which is very similar to the one you also know from kind of the optical solitons and fibers, but actually has two very important distinctions. And that is, there's a loss term. This resonator has loss, so it's losing continuously energy, and the system is driven continuously. And so these solitons actually are called dissipative solitons because they are solitons of an open system, of a system that loses basically energy to the environment. And so the way the soliton formation proceeds is you tune the resonator into resonance, you start to generate these so-called Turing rolls, then a chaotic regime, and then in a moment where you tune across resonance, actually all the waveforms collapses into either one or multiple solitons. And you can switch actually from 5 solitons to 4, all the way down to the single soliton state. Now, let me just mention that this soliton formation is truly a fascinating phenomenon in the sense that what happens in this resonator here is that you can take this nonlinear Schrödinger equation with cavity loss, detuning, and drive, and you can map out and numerically compute the solutions. And the solutions you can draw actually in a two-dimensional map. One is the power that you inject in the resonator, shown on the vertical axis, and the detuning of the laser on the horizontal. And if you compute for every configuration of detuning and power the solutions that these equations admit, you will find actually that there are regions where you have chaotic waveforms, regions where you have stable solitons, and regions where the solitons can breathe. And this is an example actually of a much wider class of phenomena that have been termed in chemistry dissipative structures. And if you look around in the world, what you find is pattern formation. Pattern formation is ubiquitous, from sand dunes to clouds, okay, to stripe formation to chemical reactions. So every time you have a system that is driven strongly, has nonlinearity and dissipation, actually pattern formation is a naturally occurring phenomenon. There are regions where patterns can occur. And patterns in frequency metrology imply coherent pulses that are fully coherent and give rise to an optical comb. And so we study actually this pattern formation and these dissipative structures in these microresonators based on the Kerr linearity. Now, the next question is, can you generate actually this dissipative Kerr solitons also on this new platform of silicon nitride? And so this is an example of some of the early work where we demonstrated that it's possible to generate a Kerr frequency combs in silicon nitride. And what's striking in silicon nitride is the vast bandwidth that we can generate. We can generate spectra that are octospanning. We can cover the entire telecommunications TNL band, but the mode spacing here is very high. We can have mode spacings of 10 to even 100 gigahertz or even more. And we can model actually these based on this nonlinear dissipative Schrödinger equation. Inside the pulse, you have solitons locked to a background, which can also be very short. In this case, actually, it's a pulse that's about 25 femtosecond. Now, in its early works, however, one of the challenge was the quality factor of the resonators. So these early solitons actually were demonstrated with 10 watts of optical power about a decade ago. And this was because the quality factor of silicon nitride initially, okay, was too low to support very low thresholds. And what has happened actually is that the threshold of these soliton generation has now come down actually to just a laser pointer. You can generate in silicon nitride these carrier frequency combs with literally powers of just a few milliwatts. And this is because the optical quality factors have improved actually by more than a factor of 100, and that gives you a factor of 10,000 reduction actually in the optical threshold. And so what is this allowed to do? You can generate also these dissipative carrier solitons at very low microwave repetition rate frequencies. So this is an example of a silicon nitride K-band and X-band generator. So it puts out streams of solitons at 10 gigahertz and also generates upon detection actually a reasonably low phase noise microwave here that comes in at minus 135 dBc per hertz at 10 kilohertz offset. So you can use them directly actually as a low noise microwave generator. Now, another example that has been really enabled by these very low losses that we have is the pump laser. So evidently, pump lasers of several watts are precluding use actually in compact devices. So here is some work actually that shows that if you use just a DFB, a distributed feedback laser, that has an output power of typically 10 to 100 milliwatt, and if you injection lock that to one of the silicon nitride resonators, the slight reflection that you have from residual imperfections leads to two effects. The first is actually it will send back some of the power into the laser. This leads to a phenomenon called self-injection locking, where the free-running DFB line widths get suddenly dramatically narrowed, and I'll mention actually how much a bit later in the presentation. But there's something else happening. You can also, on top, generate actually a soliton. So these are so-called self-injection locked carrier microchromes that now actually have a form factor of just a few square centimeters, and also can be driven here with electrical powers that are in the watt level. Now, to give an example of, if you want to dream further, what's the most compact kind of chip-scale comb that you can possibly imagine? This is some work we did with John Bauer's group, where the pump laser was heterogeneously integrated. And so what you see here actually is a silicon nitride wafer. Okay, there's a so-called interposer made from silicon to take the light from the low-loss silicon nitride into a 3.5, in this case a 3.5 epi, that has been structured to make DFBs. And the entire device here has a length of 500 micron and a width of 100 micron. So literally it fits actually on a needle tip. And the total wafer here contains more than 3,000 microchromes. Now, admittedly, these microchromes are not self-reference frequency chromes, but still they do produce optical comb spectra with 100 gigahertz mode spacing. And this shows you the tremendous kind of benefit of scalable manufacturing to make very large volume kind of microchromes that potentially one day you could use also in optical transceivers. Now, what are the applications of the chip-scale microchromes? It's not just the compactness that makes them interesting, it's really this large mode spacing. And this large mode spacing is interesting and imperative for astrophysical spectrometer calibration, where you have only a limited kind of resolution power of the spectrograph, incoherent optical communications, where the channel spacing is inherently a multiple of 12.5 gigahertz. You can also realize ultra-fast distance measurements, dual comb spectroscopy. You can make a clockwork for clocks, photonic radar, low noise microwave generation, and also more futuristic applications like neuromorphic computing. So there's a large kind of list of applications that have been explored by us and many in the field that really show kind of the virtues and advantages actually of this large mode spacing microchromes in this very compact setting. Now, in addition to the vast applications, let me still mention these devices also are fascinating just in their own right, and I will not discuss it much, but I'd like to mention that you can also look at very complex nonlinear phenomena. Even though we have studied the single resonator case in much detail over the past, say, decade, already if you add two or three or a whole array of optical resonators, you can generate very complex nonlinear interactions. And so in some sense, these microresonators, what they are basically analog simulators of partial differential equations. And by scanning a laser, you can look for kind of coherent solutions in such a system. And over the last years, we've shown that, for instance, already adding other dispersion terms, higher dispersion, normal dispersion, mode crossings, you can generate not just bright solitons, but a whole family actually of dissipative structures that we call platicons, so switching waves, and that we call also zero dispersion solitons, because they live in landscapes that are almost dispersionless. So our understanding of solitons has really evolved, and we now understand that any driven dissipative system that is nonlinear can generate coherent waveforms. It doesn't have to be an optical soliton itself. Now let me switch gear and more to the application side again. We have these very low loss integrated photonic circuits. Can we make frequency agile lasers? And so this is work we've been doing with Sunil Bava over almost a decade now. And our aim was to combine technology that's very well known, that's actually so-called aluminum nitride, F-bar, H-bar. So if you have your cell phone, these actually use filters that are made from piezoelectrics. And these can be, these are foundry compatible materials that you can also integrate onto silicon nitride integrated photonic circuits. And so the way that the integration works is shown here. So we have an optical mode that sits in silicon nitride, and we have the piezo actuator actually removed from the optical mode, sitting on top here, shown in green. And so what actually are we using here? We use actually the stress optical effect. That is to say that once you apply actually a voltage to the top and bottom electrodes of the actuator, you generate a stress, and due to the finite Poisson ratio, you create an in-plane shear. And so what happens here is that due to the elastic compliance and the elasticity-dependent refractive index, we change the optical path length. And aluminum nitride is a wonderful material for this purpose because there's a very low leakage current. It's very commercially used. It's highly linear, so it's hardly any hysteresis, very low power, and it's an available foundry process. And so we've combined this with integrated photonic circuits and thereby create lasers that we can tune very fast. And so how does this work? There's multiple ways to realize these lasers. This is one of them. And we return to this topic of self-injection locking. So we have here a microresonator that now has an aluminum nitride actuator. The light that is reflected back into the diode locks over a certain range that is called the self-injection locking range. That can be several gigahertz of bandwidth. And if we now very quickly actuate actually the resonator frequency, we can achieve a frequency agile laser that is highly linear with very low power. So actually, how well does this work? Let's first look at the laser line width. One of the surprising aspects of these lasers is that due to the very high quality factor, these lasers operate basically at a thermodynamic limit of line width. And where does the thermodynamic limit come from? It comes from temperature fluctuations. So ultimately, these self-injection lock lasers are limited by frequency noise that is uniquely determined just by the temperature fluctuations of the material itself that are innate to the thermodynamics. It's called thermorefractive noise. And the thermorefractive noise we can engineer by simply making the cavity longer. We can reduce the noise process. So you can see here from green to red to blue, actually we are making longer and longer kind of spirals and achieve a phase noise here, as I'll comment, that can even be lower actually than the phase noise of a fiber laser. So this is a result actually that surprised us when we first measured it some years ago. So what's shown here is the frequency noise spectral density of a fiber laser from NKT. So it's a workhorse kind of for fiber sensing. And what's shown here actually is the phase noise of one of these high Q aluminum nitride endowed optical resonator that we use for self-injection locking to a DFB. What you can see here actually is that we can operate actually even below the phase noise of a fiber laser. And this really shows that integrated photonics now is making a step not only from being compact, scalable, and manufacturable, but the most important aspect about integrated photonics now, based on these low-loss materials, is that we have performance that inherently challenges like traditional laser systems. And that makes actually this technology really useful. Now the other aspect is how fast can you scan with the piezo actuators? In fact, if you suppress all the mechanical modes of the chip itself that can get excited, we can have a flat actuation response up to 10 megahertz with the piezo. That's actually this blue graph here. And this shows actually an incredibly fast kind of tuning that we have due to the use of piezos actually as an integrated photonics technology. So again, to be contrasted with bulk piezos in lasers that typically scan like a few kilohertz at most. And we're only limited here actually by the acoustic resonances of the photonic stack itself, which sets in at about 15 megahertz. Now, what can you do with this type of lasers? Just give me one example of one application. And this is an application called FMCW LiDAR. So FMCW LiDAR is a perception technology that has some very advantageous properties. It allows you to measure in every point not just the distance, but also the velocity. And the way this works actually is by sending out a laser that is frequency chirped in a triangular fashion and beating it actually with a replica of the signal, okay, at the laser. So it's a beat note that you generate. And as Art Shallow said, never measure anything but frequency. Of course, very well known saying to this community here. FMCW maps both the distance and velocity actually of an object to actually a frequency. And that makes it stand out in terms of LiDAR technologies. But it has one challenge. You need very linear lasers for this, with highly linear kind of chirps to actually generate the beat note. And this can actually be done using this aluminum nitride due to the high linearity of the actuator. And this shows actually a very simple point cloud here of a ring and donut that we've mapped in the lab actually using this aluminum nitride endowed low-loss indicator photonic circuits. Now last, silicon nitride is transparent down to the visible. In fact, the lowest line width we have shown is 369 nanometer together with Park semiconductors, now called SRI, Thomas Wundra. Other wavelength we have shown is 410, 461, 517. So you can really see that these circuits can not only generate frequency agile lasers at 1550, but also be used to actually create very compact lasers that can, for instance, be used to stabilize for optoatomic clocks or for repumpers in a compact form factor. Now, in addition to making low-noise lasers, the low-loss integrated photonic circuit based on silicon nitride can also be used to make amplifiers. Because in many applications, you need to amplify also signals. One of the key technologies that have been developed in optical amplification is the development of the Erbium doped fiber amplifier. So this was developed already in Schnitzer in the 60s, then Desavir and Sir Henry Payne demonstrated the first Erbium doped fiber amplifier in 1986. And this really triggered the revolution of optical communications. It allowed actually to replace electrical repeaters by optical ones and also to amplify data streams across transatlantic channels. And the advantage of Erbium actually is that it's a gain material that has low interchannel crosstalk, so it can amplify data channels, very low noise figure, close to 3 dB, and also it's temperature insensitive and can be readily incorporated in a host matrix like glass while retaining its atomic-like properties. So the question is, can you make Erbium doped amplifiers also on chip? And why is this challenging? It's challenging because Erbium actually gives very low gain. So the gain of Erbium, even in a high concentration limit, is typically on level of dB per centimeter. So what you need is a host with very low optical losses. And so what we've recently demonstrated is that by using silicon nitride and using ion implantation, a very well-established manufacturing step in the semiconductor industry, we can implant Erbium ions inside the silicon nitride waveguides while retaining their very low loss, and thereby have very good optical overlap, as shown here in the Rutherford backscattering, of the silicon nitride waveguide mode, as well as the Erbium concentration profile. And what this allows to make is actually very compact amplifiers. So it shows an amplifier here, it's a spiral that's 50 centimeter long. The chip here is 5 millimeter in diameter. And we get optical powers here that are more than 100 milliwatts. And so that's really comparable to what you can obtain like with a small benchtop optical fiber amplifier. So again, we are now nearing a performance level that becomes interesting already for systems. Now, where could you employ such very compact Erbium amplifiers? Actually, one application, okay, is pluggable optics for data centers and data center interconnect, where also you need to amplify, okay, inside a very small package, the optical signals. And so one example, there's joint work actually that we did with Nokia Bell Labs is to amplify channels for data communications. So here's an example from my own lab where we show 100 gigahertz microcomb in red with very low power per comb line, much below minus 20 dBm, so we can't use it for communications. We run it through our Erbium doped waveguide amplifier. We can conveniently push up all the optical modes to more than 0 dBm, so 1 milliwatt. And we've also demonstrated actually this together with Nokia, really that this technology can also be used really for multi-terabit per second optical communications of actual data containing signals. Now, so what can you do with these Erbium doped PICs based on silicon nitride? I've given an example of amplifiers, but it's only one example. So you can make single frequency lasers, and also in the future you can even make mode lock lasers based on Erbium directly on chip and utilize the Kerr nonlinearity for mode locking. And to give an example actually of a single frequency lasers, so this is an example of how such a single frequency laser based on Erbium can look like. You see here a silicon nitride circuitry. You see resonators that form frequency selective elements that you can tune very fast with either heaters or piezoelectrics. And you see here selectively implanted erbium gain. So that's the rendering. The actual chip looks like this, and you can do selective implantation only in regions actually where the erbium needs to be. In this case, in our long gain spiral. And you see here the circuit layout, including the verniers and the reflectors. And with this, actually, we can make lasers that are fully tunable across the CNL band, very high side mode suppression ratio, and also come in with reasonably low phase noise. So again, showing that you can make erbium dope waveguide lasers that have the same kind of performance as conventional ITLA lasers used in telecom. Now, in the last kind of 5 minutes, I'd like to address one remaining question, and that is, even though we have now these very low losses of silicon nitride that allow us to make carrier frequency combs, frequency agile lasers by employing piezoelectrics, there's one property that silicon nitride does not have. Silicon nitride is not a material that has a Pockels coefficient. And materials with Pockels coefficients are materials that allow to make optical modulators, which is also a key component in many kind of applications in science technology. And so what I'd like to mention at the end is how we can create very low loss integrated photonic circuits based on a new class of material, ferroelectrics, in particular lithium niobate and lithium tantalate. And so first of all, what is interesting about lithium niobate and also lithium tantalate? These are materials that have, as I said, a large Pockels coefficient. And so what this allows them to be used for is modulators. And the modulators based on silicon and indium phosphide typically have a limited bandwidth of about 40 gigahertz. With thin film lithium niobate or lithium tantalate, you can have bandwidth that theoretically even extend to 300 gigahertz, so vast bandwidth. The other aspect is that due to the large Pockels coefficient, the switching voltage actually for lithium niobate and also lithium tantalate can be actually sub-volt. So they can make a new class of optical modulators is very compact, wafer scale manufactured that can challenge both silicon and indium phosphide in terms of performance. And so over the last decades, there's been really tremendous interest in lithium niobate. So lithium niobate was once hailed the silicon of photonics. It was studied extensively in the 70s for its ability to make optical modulators using a process called proton exchange. So you can diffuse protons, actually, or titanium inside lithium niobate to make bulk optical waveguides. And a seminal turning point was actually about 2018. And that turning point was triggered by the availability of thin film lithium niobate and insulator. And that has been developed by Zola in Paderborn in Germany. There's been a Chinese company that has used this technology called NanoLen. And NanoLen has made smart cuts, so ion sliced lithium niobate and insulator commercially available. And very shortly after that commercial availability, the first results came out from Harvard, my colleague Marco Loncar, showing that you can make modulators out of this material that have switching voltages that are CMOS compatible with bandwidth that can reach 100 gigahertz. Now the challenge of the material, however, is it's very hard to etch. And as you see also in this image, typically you don't have fully etched waveguides, strip waveguides, but you have these slight protrusions. And these protrusions are really a direct manifestation of the inertness of the material and the difficulty of etching the material with conventional kind of etch chemistries. And so what we've worked over the last years is kind of two ways actually and two outstanding challenges of the material. The first is I'd like to present you like how you can make truly integrated photonics, fully etched waveguides in lithium niobate. And the second question is, can we go away from a material that is a specialty and only actually available using very few kind of vendors in the world, including NanoLen in China, and can we go to a material that's already commoditized? Silicon nitride, okay, SOI wafers, it's a commodity. Is there something similar in the world actually of ferroelectrics? And in fact there is. And there's a material called lithium tantalate, and lithium tantalate is a material that has almost exactly the same properties as lithium niobate. So why was lithium tantalate not used for optical modulators? It wasn't used because titanium indiffusion actually in this material occurs at a much higher temperature. And so that's why lithium niobate was favored. But the material has lower birefringence, higher damage threshold, and also wider transparency window. And on top of this, this material is used commercially in Wi-Fi. In fact, your phone may already use lithium tantalate filters, okay, for 5G, 6G, which require higher K-squared for the larger passband. And so the question is, how can you etch lithium tantalate or lithium niobate? And so what we've discovered and what we've used in my lab is a material that many of you may have used this morning inadvertently. So for instance, if you shave in the morning, your razor blades have a material on top of it that's called DLC, diamide-like carbon. So diamide-like carbon actually is a material that can be generated by methane decomposition. So very easily in the reactor. It coats conformally. It has the hardness of diamond, so strong sp2 hybridizations in carbon, and can be used as a coating for medical devices, tools, automotive components. But it has one very beneficial property when it comes to integrated photonics. It has an extremely good hardness. So if you compare the hardness of DLC compared to lithium niobate, it's actually substantially harder. And so this means it's a very good hard mass to etch this material. And so what we've shown actually that with this material we can etch deeply actually confining waveguides with almost vertical sidewall. And what's even more interesting, we can get very low optical losses. So losses actually of the level of basically less than 10 dB per meter. The best losses we see are 3 dB per meter, which is almost on par with what we can do with lithium niobate. And this we also commercialized, as said, with a pure play foundry, Luxelligence. This is an example of one of these devices. You see a spiral here that has a pass length here of 3,900 millimeters, so it's a long spiral, very compactly wound due to the tight confinement. And you also see here microresonators with quality factors actually close to 10 million, okay, in this material platform. So what can you make with this? First of all, high-speed modulators. So we've shown modulators with, this is actually old data, we have shown bandwidth with Christian Kruse's lab up to 110 gigahertz, so state-of-the-art compared to also what can be achieved in lithium niobate. And you can get switching voltages in the level of several kind of volts. Now, another device you can make are electro-optic combs. So instead of using a Kerr comb generation mechanism, you can make an electro-optic comb by just driving a modulator very hard or resonantly enhancing it. And here is an example of a lithium tantalate EO comb that comprises more than 1,000 comb lines, okay, driven with actually 7 watt actually of RF power. So the span here is significantly enhanced compared to lithium niobate because you have lower birefringence. Now, what is our own scientific application that we have in mind? So why are we so interested in these very low loss lithium tantalate integrated photonic circuits? Our own motivation stems from a problem in a new disguise, which is that of cryogenic interconnects. And so there's tremendous advances and tremendous interest in quantum computing at the moment. And the leading platform actually is based on superconducting circuits as pursued by Google, Rigetti, or IBM. And so if you look actually in one of these dilution refrigerators, what you see is you see literally hundreds of coax cables actually that go down, okay, from room temperature all the way to the mixing chamber. Now, what you need to know about coax cables is they are excellent conductors for microwaves, but also excellent thermal conductors. And that means that with every microwave cable that goes down actually to the 4K stage, you have about 1 milliwatt actually of heating that comes from the environment due to thermal contact. Now here actually optical fibers are very attractive. Optical fibers are excellent optical transmitters of radiation, but they are perfect thermal insulators. And so the amount of power actually that you draw from the environment by putting one optical fiber in your fridge is less than 10 microwatts. And so this problem is very similar to the data center interconnect problem, where you replace copper cables by optical interconnects. And the question is, can you do the same for superconducting circuits? Now, what you need to achieve to do that, what you need is one element, which is the optical modulator that will take actually the RF signal from the superconducting circuitry. The qubits operate typically at 5 to 10 gigahertz. But in order to convert that to an optical signal, an optical modulation, you need an exceptionally efficient optical modulator. So to replace a conventional hand amplifier, you need to operate actually with switching voltages well below 100 millivolts. So this needs to be a modulator that you can switch basically with your heartbeat. Now, the only way to realize these actually is to have a very long interaction length. And this can be achieved actually if you take, say, a 55 centimeter lithium niobate or lithium tantalate integrated photonic circuits. With this actually you can get switching voltages in the tens of millivolts. This is an example of such a device. It's a 20 centimeter long kind of device. In lithium niobate, and this can operate if you go to 1 meter path length with a noise figure actually that's very close actually and even below the one of the hand amplifier. And so we believe this is one of the kind of potential interesting, say, scientific applications actually of this very low loss ferroelectrics, in addition to the myriad of applications that exist in transceivers, data centers, or LiDAR for these electro-optic active components. With this, I'd like to summarize and say, yeah, next generation integrated photonics is really ongoing in many labs around the world, enabled by these new materials, these optical losses that are coming down in the single-digit dB per meter level. and also allows actually for new technologies to be created. And these are just some of the spin-offs from my lab, but there are many other spin-offs in the world actually that are capitalizing on this wave of development. And with this, I'd like to thank again the organizers for inviting me, and also you for your attention. And I'm happy to take any questions in the break.
Thank you very much, Tobias, for this fascinating talk, and congratulations for the great work you have been doing. So I'm sure there are a lot of questions in the audience. Please. It's great for the microphone.
Are you at all concerned with some of the optical isolation needs while doing these platforms? Are you seeing the lack of?
Yeah, it's a very good question. So the question was, what about isolation? In fact, there's something very neat I'd like to mention. So the answer is, for the integrated lasers, what has been now established in the community by work from colleagues and others in the field, is actually that these self-injection lock lasers actually are very immune to, and the same actually also true for microchromes, are actually immune to backscattering to a large degree, so without even using an isolator. And let me explain why. So if you have a microresonator, okay, then what actually happens here is that you have the non-linearity. So the moment the laser actually locks and self-injection locks, what happens is there's a cross-phase and self-phase modulation in the resonator happening. And the cross and self-phase modulation actually have different strength. And what happens is actually the light that is back reflected, that sees not the clockwise mode but the counterclockwise mode, actually is detuned from the resonator. So stated differently, a strong laser field, okay, that circulates preferentially in one direction creates actually an artificial kind of flux. It breaks symmetry. And this you can exploit actually to make these lasers inherently kind of not very susceptible to back reflections. And this holds for any device that operates with high power, so self-injection lock lasers, but also microchromes. So there actually we do not see back reflections matter. Where they matter is in Erbium amplifiers. So there it's actually very clear. So our gain, if you have a 20 dB gain on chip, and you have just 7 or 8% reflection in the facets, you start lasing. So on-chip amplifiers based on Erbium, okay, will actually face our sensitive back reflection. If you use nonlinearity like traveling wave parametric amplifiers, you again use the kernel nonlinearity to break symmetry and become less sensitive to back reflections.
Another question? So thank you for that talk. And I would like just to have your point of view. We have seen different components, different materials, a bit of an integration. What is your point of view of the integration of these different components, materials, and microelectronics?
With
Microelectronics also. So do you see an issue in the integration of?
Yeah. So I think I would answer the following. So I think there's one, I would say. So the question is, would it be a benefit, if I understand you correctly, to integrate with further electrical and optical functionality and make really complex? And here, I think we can learn from the past. So people have tried in silicon photonics to have silicon photonic components directly sitting next to CPU and CMOS, and really try to co-integrate optics and electronics. And that's very challenging to co-integrate optics and electronics on, say, the same chip. Because you're always faced with the choice of materials that need to work for electronics, work for the optics, with thermal heat management. I think we're now these next generation, as I like to call them, integrated photonics is making a difference, is really looking at targeted applications where the performance is, say, superior or is unusual. Microchromes being one example, very large mode spacing. So there, even without adding any other functionality, it allows to address both scientific and technological applications. Another example are these record low line width lasers that can be used for fiber sensing. So if you want to have a fiber sensing interrogator that's handheld. So I think the beauty of these devices, at least from judging the past, probably lies in creating, having one performance where they're very good at, the laser phase noise, the optical comb, the very compactness of the amplifier. But integration, integrated photonics is always a challenge. So if you try to make a very complex system, have an optical clock, then I think you start to multiply probabilities. And that's why I would expect the first applications that really penetrate the market to be very simple ones, like a very low noise laser, amplifier chip, microchrome chip. And probably in the decades to come, the system becomes more integrated.
Is there any question?
You were saying that the type of loss that we have in this field are still very far away from what we can get. We have actually two questions. One is what is preventing the type of loss, and second, could achieve this loss, lower loss, which would benefit.
Yeah. So it's an excellent question. So I've been scientifically interested in this question, or even say obsessed with this question for now many decades. The first question I can answer is, we've demonstrated 1 dB per meter in silicon nitride. It's a fantastic value. So 10 years ago, I would never have thought this is possible. But the question is, what is the ultimate limit of silicon nitride? And so there we have made measurements without going into how they work, but we can look at what the residual absorption of the material is. And actually it turns out that we are more than 2 orders of magnitude away from the fundamental limits of silicon nitride. So silicon nitride should actually support, based on the optical measurements we have made, losses actually that are 0.001 dB per meter, so basically 10 dB per kilometer loss. I can pinpoint one of the sources of loss. That's a loss that is very well known also here in Neuchâtel, because a lot of solar cell industry here. We see actually that inside silicon nitride there's copper. And that copper we understand where this comes from. You need to remove that residual copper from the materials that comes from the processing. And if you can remove that copper, we believe that we can probably get another, maybe factor of 10, maybe of 100 improvement. Now, what would this allow to do? The first thing you could do with a factor of 100 improvement, you can make traveling wave parametric amplifiers. So I haven't talked about them much, but the traveling wave parametric amplifier is a beautiful and actually amazing device. By just taking a waveguide and just pumping it CW, you can generate broadband gain. And if you engineer dispersion of waveguides, you can generate an amplifier with 30 dB gain that's completely unidirectional, so rather insensitive to back reflections, with a bandwidth of 60 terahertz. And so what is 60 terahertz? That's 10 times the Erbium gain window. And so you can make a completely new kind of parametric amplifiers. People have been dreaming of those in fiber optics in the 70s. They suffered from too low linearity. With these low loss integrated photonic circuits, with another factor of 10 to 100 improvement, we could make 2-pass actually, and that are really deployed in systems. You can make even narrow linewidth lasers. You would have, so the coherence would still improve. So I think those are the two applications where even going to lower losses can unlock new applications.
Thank you for the great overview. I'm curious, for your microphones for applications for optical clocks, could you speak a little bit about F-to-2F locking, self-referencing, and then maybe impacts of thermorefractive noise in optical clock applications?
Yeah, so it's a very good question. So an expert question. Your question was, first of all, about F-to-2F. So one of the, challenges, and still ongoing challenges, I think you can use the spectrum here as an example. You can generate octave spanning spectra in microchromes. The challenge is, first of all, you need power for doing F-to-2F, and so what you can do is you can use so-called dispersive wave, which is a kind of a feature of the soliton, where the soliton actually has this oscillatory tail. And these you can engineer to be exactly at F and 2F frequencies, and there's been work by Scott Papp at NIST that has beautifully shown that you can make octave spanning combs with F-to-2F aligned, and also Kartik Srinivasan at NIST in Gaithersburg. The challenge still is that these microchromes, where they really shine at, is very large rep rates. So in some sense, making a repetition rate of a terahertz is extremely easy because the thresholds are low, but bringing down the repetition rate to a few tens of gigahertz actually causes the Soliton process to be rather inefficient, and also you need to align F2F. So if your FCO suddenly gets 50 gigahertz or 49 gigahertz for a 100 gigahertz device, it becomes challenging to detect. And that's why, say, microchromes, in terms of clockworks, they require a more complicated architecture. So you need one comb that's very broadband to give you an octave, and a second comb actually to measure the repetition rate. And this has been shown actually by, in the work from Scott Papp and Karg Srinivasan, that you can make actually a frequency synthesizer, so generate an arbitrary frequency, or use it actually in a clockwork application. Now you asked about thermoreflective noise. So the thermoreflective noise in these microchromes would be the fundamental line width. So if you look at a Soliton pulse stream that comes out and it was not stabilized, that pulse stream of Soliton has a phase noise that is governed actually by intrinsic temperature fluctuations of the resonator. And the smaller the resonator becomes, larger it becomes. Say for an optical clock, what would be important is the elements, is how fast you can lock the comb. And this actually can be extremely efficient if you use these piezoelectric actuators. So if you had an optical clock application where you really want to transfer the phase noise of your primary laser line to the care comb, this can be done very faithfully actually, using the piezo actuator and laser frequency as two independent control knobs.